Hoy tenemos aquí a Didier Queloz. Él es una de las personas más importantes en el campo de los planetas que se están descubriendo fuera de nuestro sistema solar, los llamados exoplanetas. Didier es, además, una persona honesta, un científico magnífico, con un entusiasmo increíble. Es realmente alguien donde se junta la candidez de la ciencia con la precisión de la tecnología de punta. Y esa combinación da lugar a resultados sorprendentes, resultados que nos dejaron mudos a la comunidad científica cuando Didier y Michel nos presentaron el descubrimiento en 1995, en octubre de 1995, en Florencia, el descubrimiento de un planeta que giraba en una órbita muy próxima a una estrella muy similar al Sol. Y durante un momento nadie pudo reaccionar, realmente fue un impacto tremendo que es algo que se siente incluso en este momento. Notamos esa energía, esa ola que nos trajeron Michel y Didier. Y hoy tenemos, bueno, Didier, gracias a este programa, a la Fundación del Banco Bilbao Vizcaya, y este programa que hoy renace con Didier, el programa de la Fundación. Gracias a la Fundación, pues, vamos a poder disfrutar de la charla de Didier, que además de un gran científico, es un magnífico comunicador y nos va a contagiar su entusiasmo, no les quepa duda. Y bueno, creo que ya me he extendido suficiente y voy a dar paso al gran protagonista de hoy, que visita Madrid por primera vez. Está muy contento, lo han tratado muy bien, no tan bien como para decirnos cuáles son sus fuentes secretas que tiene en la cabeza, que le dicen a dónde tiene que apuntar el telescopio. Creo que todavía no ha bebido lo suficiente para decirnos esos secretos, pero nos va a contar muchísimas cosas fascinantes de este campo, que sin duda es uno de los campos más hirvientes, más atractivos de la ciencia actual. Así que, por favor, Didier, adelante. Al valor y al toro.
Thank you for being here. It's a real pleasure. I will speak in English. My Spanish is not well enough to give such a lecture. I can understand a little bit, but not really talking with that. Hello to some of the people I know in the room. It's a pleasure to be here. So we will have a tour. It's a kind of fascinating field, this exoplanets that we are in, that deals with planets on other stars. And it's a very young subject. It's a very fast evolving subject. And there is a lot to say on this. So I had to make some selection, some choice, and I decided to take you with me in a tour on this new world of the cosmos, and trying to give you a little bit of perceptions why we're so exciting about this, why it is so important to us to understand these new worlds. So before going to the new worlds, I mean, let's talk about something that is known, which is our solar system. Actually, we believed we know everything about the solar systems. We thought that we understand how the solar system is formed. we thought that we understand all the details, and there is something that comes with these new planets that is now found on other stars, so they're very far, that tell us more about our solar systems. And one day, all these detections will also tell us something on the life, on the Earth. I mean, is the life unique? How the life started? I think part of the answer will be by looking at other planets. We can look at Mars, but you can also look on other planets, on other stars. So to give you a little bit of a feeling, when you talk about planets, you talk about details in the universe. And if you see here, it's just the side of the sun. The sun is huge. It's basically the size of this whole wall here. And the planet is very tiny here. It's 10 times in size of the sun for the big one, for the Jupiter, this one. You recognize Saturn, obviously, with this ring. In terms of a quantity of material you have in a planet is also almost nothing. You need 1,000 Jupiter to have the same mass than the sun. So it's really just a detail. It's less than 1%. It's 0.1%. Jupiter is, in terms of what is in, it's not very far from the sun. It's basically hydrogen. It's mostly a lot of gas you have in these planets. It's very different when you move to the small ones, like you recognize the Earth here, which is basically rocky, only solid bodies. This tells you also how many rocky body, how many solid materials you have in the solar systems. Actually, most of the material is in terms of gas, is hydrogen, and there's only a little bit which is rocky. But that's a very interesting one because it's one where we are in right now. So, in a general sense, planet is just a tiny detail when you form stars. And if you look back, what we understand of the formation of these planets, you find something quite interesting. If you look a little bit from farther out on the solar system, this is an artistic picture. You not only have all the planets that I mentioned before, but you also have a lot of materials, small bodies. Sometimes we know some of them because they come very close and they make nice comet. And they are quite numerous. They are small and quite numerous. And they are the fossil of the time when the planet forms. And it gives you a little bit of the idea how we understand the planet formations. You have the stars that forms, and then a little bit that remains is around the stars. And this little bit is like a plate, a disk, and from this disk you start to agglomerate and to glue and to form planet. And some of them are too far. They have no time to glue, and they stay like that. It's basically kind of snowballs, ice balls that you have here farther away. They are beyond the Neptune's orbit, and they are very often called trans-Neptunians, for those of you who know these names. So this was a very important piece of information that came up about 10 to 20 years ago when we started to discover all these small bodies. It also was a kind of revolution because we realized that Pluton, which is this one, is just a kind of trans-Neptunian object. And that's why you may have heard that Pluton is not anymore seen as a real planet like the other one, because it belongs to this very numerous number of objects. So if you want to understand a little bit how fits the planet, there is a big scenarios where the planet enter, which is called the cosmic scenarios. The cosmic include a lot of the raw material you have in the universe, which is basically the hydrogens. And this is there's a lot of gas, gigantic cloud of gas, hydrogen, very primitive gas, the one created at the formation of the universe. And some of these gas sometimes start to agglomerate, and you get this kind of dense, gigantic, it's called molecular clouds. And from this, you can form stars. It's just the gravity. Gravity attracts things together, and if you have enough gravity, enough bodies, they start to agglomerate. And then one day you may get a star, and with something around it, and from this something you will get the planet, and that's what you get here, and at the end you get this small body. So the planet is a kind of the end product of the formation of the stars. It's very connected to the formation of the stars. And we do believe that basically when you form a star, you must form planet. It's kind of expected, and it was expected from the early days when we start to understand the formation of the solar system. And that was on the very first question that people start to answer when they were looking for other planets and other stars, is whether this was real, this was true, that you form planet out of a star, of any star you form. So to give you a little bit of a picture that things is a little bit more complicated than that, this is a star formation process that is simulated in a computer. It's a lot of gas. It's a big cloud of gas. And what you do see here is the gas is just falling together and will gradually accrete and condense. You will zoom to see more detail. And you zoom on detail and you zoom on density. And so slowly you will build up the stars. Pay attention to this number, which is the age of the system. It's a very young system. Here it's 100,000 years. For astronomy, it's very young, 100,000 years, because the universe is almost 14 billion years old. And you do see here the stars that forms. They form in a very complex way because they touch each other, they bounce, and you have a series of stars formed together, just ejected. And that's why we do form the stars in clusters. The star doesn't form alone. There are a series of stars. You see all this, and you continue to form stars. So what you have to imagine in this scenario is with the stars that is going to be formed, and then you see continuation of formation of stars. There may be many stars formed together. It's called multiple systems or triple systems. And on each of these stars, you can question whether there is something left that may be used after to form a planet. And that's how you have to see all this full process. I mean, the planets are really connected to these stars. So people are trying to look in systems whether they found trace of planet. And there is a very famous site where we know there is a lot of stars that do form, is Orion. It's a very nice place to look at. If you have a small binocular, just have a look. You will not see this because this is done with a space telescope. But you will see something already nice just with binocular in Orion, and you see that in winter. And when you look into this, if you do zoom, you do see that there is some fraction that looks like there is a star with something in between, just around it. And if you zoom in on some of the objects, and that's what I'm doing here, you basically see that here one of the stars is surrounded by something which looks like a disk. So in the universe, we have plenty of this kind of young stars that have disk, similarly to the disk I mentioned before when I talk about the solar system. I tell you there is kind of a fossil of a disk in the solar systems. So we have all this, we have picture of this, and then the question that you do ask is whether there is planet there. So before answering that, I need to bring you a little bit into a subtlety on the formation, a detail on the formation that has all this importance to understand why, when we make the first planet, it was such a breakthrough, such a shock for the community. This is the same kind of picture I showed you before with the planets. And when you see the sun here, and when you see the different planet here. There is something that should be striking to you, is if you look at this sequence, the distance is not right, but the sequence is right, is you have the small planet, rocky planet, close to the star, and you have the big one a little bit away, and if you go too far away, there is no planet anymore. You just have this kind of called dwarf planet. It's called this trans-Neptunian object, where you have a couple of them known. And there is a famous Eris discovery that gave rise to this big debate on what is a planet, what's not a planet. And what is important here is you can ask why. So why the Jupiter here and why the Earth are here? So to understand that, I have to bring you a Swiss picture. In Switzerland, if you live in Geneva, for example, you live close to the lake, it's down. But when it's raining at Geneva, very often it's snowing on the mountains. So what you do have is this. It's a picture that I took from the Jura. It's very close to where I'm living. So there is a boundary here, which is a boundary between the water liquid and the water ice. Snow is ice, it's exactly the same. It's a very important, interesting limit. This limit is always computed, and every day when you're in Switzerland, they tell you, be careful, at this altitude you'll get snow and you don't get snow. This is kind of snow line here. You get exactly the same in the solar system. It's not exactly a snow line like that, because the water in the vacuum cannot be liquid. The water in the vacuum is either gas or the ice. You don't have liquid in the vacuum. It doesn't exist, these states. But you have the same situations, because you just rotate this like that, and then here you put the star, and then here you put the planet. So basically, you end up with a situation where Jupiter or Saturn are in the area where it's very cold, when there is a lot of ice, while the Earth is in the area where it's too hot to have ice. There is no ice there. And why it is so important is because ice is easy to glue and to agglomerate. If you build snowballs, it's easy to put the ice together. If you go to the beach with the sand, it's a little more difficult to put the sand together. In space, you can. You go slowly, and it's called molecular gluing. You just glue things together. It takes a long time. It's very slow. So basically, if you want to form a body by just sticking things together, it takes a long time here, while here it's very fast. And the time is the essence here of the process, because the gas that remains when you form a star, remember, you always form stars, and you form stars from the gas, which is here. There is a little bit of gas that is around, but these gas disappear fast, typically 10 to 20 million years old, which is fast in terms of astronomy. So if you want to build Jupiter, which is basically gas, you need to be fast. So you very fast build your snowball, and then your snowball becomes big enough, and it's like a vacuum cleaner. You start to accrete all the gas around and makes a big planet. And that's why we understood that Jupiter is here. That's why, in the mind of everyone, a big planet has to be away from the star. It cannot be close because of this ice line idea. And the ice line turns out to be about right, 3 times the distance between the Earth and the Sun. So this was a real surprise, as you know, when we started to discover planets, because you will see that, but we start detecting planets like Jupiter, but not farther out. They were very close to the stars. It was a big shock. So before going to that, I just want to spend just a couple of minutes to explain how we did this first discovery. So the principle, when you have a planet orbiting a star, what happens is the planet makes a big orbit, but the star has a little bit of motion, a little bit. What you can do is you can compute the speed of the star. So while the star will be moving, the star will be moving a little bit behind and in front. Then it will change the speed. This is what you see here. The speed of the star is changing. Actually, you can compute the speed of a star using the pattern of the light of the star. It's called a spectra. You build a spectra from the star, and this motion you see here, you can measure it. You can measure these motions due to a planet. So you don't need to see the planet to detect it. It's enough to detect the effect of the planet on the star, and that's the kind of technique you can use. The trick is, this is the old techniques. The first speed measurements of stars, it's called radial velocity, it's a technical term, but you can say speed is fine, is more than 100 years old. It's a real old idea. And when the people start to do the first speed of star, they said, well, we could use that for the planet. So there is nothing magic in this. The problem is the scale of what you have to measure. So in astronomy, we do this kind of spectra. It's like a book. So when you take a star, you spread the light, and we spread it like a book with lines. So here you get the blue part of the spectrum, here the red part. And if you pay attention to this picture, there is kind of black line here. This is the trace of the element that you have in the atmosphere of the star. It's like a genetic code. It's like an imprint. So with this, I can tell you the temperature of the star. I can tell you how much material there is. I can tell you a lot of things. But what I can tell you here is the speed of the star, because the position of this line is very well known. So if I change the speed, I will know from looking at this. The problem is if I zoom in on this, I zoom on one of this line. The typical size here of this line, to see a motion of this line, I would need to move this line by about 1,000 kilometers per second. And a planet produces an effect only of 1,000 meters per second. 1,000 meters per second. And the planet produces an effect only of 10 meters per second. So to see any planet using this, there is no way. You have to use tricks and a lot of techniques. So this is what we have been doing with Michel Mayor, basically. We have created the techniques that allow you, using this, to see tiny, tiny, tiny change from the stars. And that's what happened in '95. Using this telescope in Haute-Provence in France, we found the variation of a planet. So there is no nice picture. This is a picture from an artist that did it. But this is the planet picture that we did at this time. This tells you that the speed, this is the speed, is changing. This is the time with time. And from this, you can deduce, you can get the mass from the planet, how heavy is the planet, and you can get the orbital time to make a full orbit. And to the surprise of us and to the community, and Eduardo was in the room the day we announced it, is this is a Jupiter kind of planet, almost, 0.8 Jupiter mass. But the time this planet takes is 4 days. And to go around in 4 days, you need to be very, very close. So you're so close that you are 20 times closer than the Earth and the Sun. And you are so close that the planet is very hot. And you may have heard about this word hot Jupiter. And this is the first hot Jupiter. And it was a shock, because from the story I tell you before, it doesn't exist. Because to form a Jupiter, you need the snowball. There is no snowball there, it's just too hot. So it came up as a real revolution into the formation of the planet, and people start to think what happens when you form a planet. And this is the kind of work that people have been doing, simulating the effect. What I wanted to show you here is when you have a planet, this is actually the planet here into the disk with the stars, the planet creates a lot of structure, a lot of patterns. It affects the disk. There is an interplay between the disk and the planet. And this creates a lot of effect on the planet. And one of the many effects that can be created is you can move the position of the planet. The planet, when you form a planet, it doesn't stay forever where you form the planet. And that was a revolution at that time to realize that the planet can move, because we have never thought about this in the solar systems. And the interesting aspect is people at that time started to look back in the solar system and thought maybe the solar system moved. Something happened in the solar system. And I will show you here a simulation of the solar system like it may have been. This is the time. This is the planet of the solar system that you see here. And this is this famous Neptune's object. There's a lot of objects, tiny objects. So what you do see if you pay attention is the orbit a little bit changing. They're moving a little bit of this planet, slowly a little bit. The problem is by moving a little bit, it may come to a position where the system becomes unstable. And when these people have demonstrated, this is people from Nice that did these simulations, after some time, here we are about half a billion years old after the formation of the solar systems. You don't see it, but it stretched a little bit because the system is a little bit moving. It will come a time, pay attention to the event, where something dramatic will happen. So there is kind of situation where there is what's called a resonant situation. It's like in the car. Sometimes you open a window and you still to hear a weird sound in the car, or there is a motion and it's amplified. When you do the kids, they love to play on and with this kind of motion, and then they can enhance the motion and they can just enhance the amplitude. It's called a resonant phenomena. And the interesting aspect of this resonant phenomena, it basically moves all these objects everywhere and projects some of them towards the solar systems. So the big question was, do we see any trace of this phenomena in the solar systems? And actually came a surprise, because you may have known that on the moon there have been a couple of missions launched 10 years ago whose idea was to measure the height of the moon, the altitudes, in a very high accuracy. to try to detect some structure that you don't see in this picture. And this is the altitude measurements of the moon. And if you look in the south, on the back side of the moon, the one that never see the Earth, the one that always see the space, the one that always see anything that may come from outside, we started to see this big depression here that was identified as a crater, 8-ton crater. It's a big one. I mean, it's about the size of 1,000 kilometers. It's a huge crater. The problem of this crater, it's on the top of the others. So the moon has been created about 50 million after the creation of the Earth. It is seen as a creation, a big impact hit the Earth and create the moon. Then after, there is a lot of craters that hit the moon, and by the time all these meteoritic start to slow down. It's a big shower of the formation of the solar system. And then after some time, this should not be anything. It should be quiet, like now, almost quiet. So why do we get such a big impact on the top of the others? Because it's in the top, it means it comes after the others. You get all the others, and at the end, it comes on the top. So we do believe that this is a creator created by this event I showed you before. The motion of the planet in the solar system that move a little bit back, Jupiter and Saturn, it's big, big motions, that completely clear all these regions and bring a big hit on the moon that created this major crater. The interesting part of here, and why the story becomes even more exciting, is, of course, if it hits the moon, it hit the Earth as well. So there must have been quite a lot of this big meteoritic that hit the Earth. It's called the late heavy bombardment in the jargon. And because it comes from farther out, it is snowballs. It is water. So maybe, and that sometimes you heard about this big debate, where comes the water on the Earth? Maybe we have water on the Earth because of this. Maybe without dust there is no water. Maybe I was not talking to you because we never had this. So this idea that planet can move was a real revolution in the understanding of the solar systems. And this created a lot of new modelizations and new understanding that you can form a planet, that's great, but there is maybe a lot of things that happen that change completely. So another surprise came quite recently when we start to get the first picture of the solar system. This is a very famous system, HA7899. The Canadian team got this picture. The star, you don't see it, they kind of erase it, but then you see these 4 planets here, the picture. The distance of this planet is much further away from the planet of the solar systems. Typically, the solar system will basically be limited to this area. So how do you get planet that far? It must be too cold. It must be too slow to form planets. So maybe they will form a little bit closer, and maybe they just move out. So you can move in and out. So you can form many, many, many different kind of planets. Because you can move them in. You can form your Jupiter farther away, but take some, move them in, and then take a small one and move them out. So we start to figure out that there is a wide diversities in all these planetary systems. So of course, there has been a lot of planets discovered since the first one. And this is a kind of synthetic way with time. This is the time here, and this is the mass of the planet. 51 Peg is this one here, and every year we get new planets that has been detected. The red dots is the one that we have found with this new machine after the first kind of generation of instrument to detect the planet by measuring the spin of the stars. We had a new generation, and one of them is famous, it's called HARPS. And the red one is HARPS. And you see that now we're getting object in 2009 and 2010 very close to the Earth. This object has just a couple more the mass of the Earth. He's very close to the stars, so it's quite hot. It's called hot Earth. But we do find this object. They do exist, and there exists plenty of different kind of objects. And we have improved so much these techniques that now we're hitting this famous magic level where we do find Earth. We're not only finding Earth, we're finding multiple systems. And give you a little bit of flavor, this is how we see multiple systems. The solar system is this one. This is a distance. So here you get the solar system, you get the 2 big bodies, Jupiter and Saturn. Here you get the planetary systems. So you have other names you may have heard in the press, like HD 40307. You know, it's 3 kind of planets between Neptune and Super Earth. JG581. This is a little bit magic because some of them may be close to an area where it could be mild enough maybe to have life. I will come back on that later. We have 55 countries. We recently found a new one. So you see there is a lot of this system that we are now finding. Some of them is very tiny planet, like HD 10180. We have this very, very small planet, almost the mass of the Earth. So we start building this knowledge of the planet. And the kind of consensus we're getting, this is all nearby stars. Some of them you can see these stars with the eyes, basically. And when you look at the stars, your chance to find a planet, especially when the planet is small, is extremely high. We have a kind of typical rate of success in detecting a planet of, on 2 stars, on 1 of them we find a planet, because we can detect the small ones. If you'd only look for the big ones, like Jupiter's, it's less, it's 5%. But if you get to the small ones, it's 50%. And we only find a fraction of them, because some of them we can't yet find them, because we cannot detect them. Like the Earth. An Earth, at the distance of the Earth, that takes 1 year to go around the stars, would produce an effect which is less than 10 centimeters per second, which is just too small now. But people is working and changing the machine, and we're working on the next generation of instruments that eventually will detect the systems. So in the meantime, after this first detection and all this detection done by the radial velocity techniques, there has been a new kind of approach, which is called a transit. So what you can do is you can just wait that the star goes, if the planet goes in front of the star, then what you do have here is a slight decrease of the flux of the stars. So the star has some flux, more or less stable, and then when you have the planet going just in front of the star, it's like a shadow that produces here, the shadow for my body. You just decrease a little bit the light you get from the stars. And these kind of techniques start to be pretty much successful, especially with this new generation of machine that is now in space, like the Kepler missions. You may have heard about the Kepler missions doing that kind of detections. So this is a new kind of paradigm that getting to these measurements get you access to. And what you get from this is the size of the planet. And that becomes very exciting when you try to figure out what means the size of the planet. So to give you a little bit of a perceptions about the size and about what you can do with this, this is a fraction of the sun. You see, this is just the sun. You can imagine the sun just very big. And then we just put a shadow, some of the planets, to give you a feeling, a profile of the planet. So we did that for different kind of type of planets. We did that for the Earth, mass, and then the Earth composition. It's silicate. Silicate is the average kind of composition of the Earth. So, and this is what would look like the Earth. This is 100 times smaller than the size of the Sun. So it's very, very tiny to get this. So if you take the Earth mass, but you change the composition, for example, let's imagine that it's not a planet of silicate, but it's a planet which is just filled of water, completely water. So because of the water has not the same density, you will have a different size. And you see the same planet here, it's slightly bigger. You see the difference? So when you get access to the size of a planet, what it tells you is the composition of the planet. You can go from the size to what is inside. And it's very important for some of them. Take, for example, the case that you find out a planet which is, it's called a super Earth, something like a big Earth, 5 times the mass of the Earth. Well, when you get the size, you know something very important. You know whether it's kind of a silicate planet, basically it's a rocky planet, or if it's just a big planet of gas. And if you want to search for life, you would have no chance to find life here because it's gas. So there's nothing that can just sustain in gas. It's too hot on the inside. While on this one, it will tell you a lot, that you have maybe a chance. And there is all the intermediate case. But for example, when you have a mixed, you can take a little bit of this one and have a water. You can have a thick atmosphere. Knowing if a planet has a very thick atmosphere or thin, it's very important for life. Because if it's too thick, it will be too hot at the bottom of the atmosphere. And the pressure will be too high, very likely to sustain life. So all this question becomes very critical these days. And from this transit, there is even more hope to get more than just the size. We hope that using this kind of event, we can get the detail of the atmosphere. So to give you a little bit of feeling, we have two situations when you have a transit. There is a time when the planet goes in front of the stars, and it's a little bit like a sunset. You know, when you see the sun, the sunset, the color of the sky is changing because the light of the sun crosses the atmosphere of the Earth. So you get a kind of a change of the light from the sun due to the atmosphere. If the atmosphere is filled of dust, you will get a very kind of pink color. So you can even deduce what is in the atmosphere just by the color of the sunset. So here it is exactly the same. Let's imagine that you observe that time, you will be able to tell what is basically inside this atmosphere, because the light from the sun will cross the atmosphere of the planet and will imprint and give you a trace. So this way you can tell, for example, if there is water on a planet. There is another event which is very interesting, is when the planet goes back. So you see that part of the planet then is illuminated, beams part of the light and back. So it's like the moon. So you can use that to get information from the surface of the planet. You get the surface temperatures. So it's a little bit like the X-ray. You do the X-ray, or you see the bones, and when you do that, you just take a picture and you see the outside. When you play with the two techniques, you learn a lot about what is made the atmospheres. You can even think about detecting change in the atmosphere, especially using this event, because then you can follow how the light goes, how the light is reflected along the orbit. And there has been an example when a planet, people have identified that there is a big spot, hot spot on some of the planet. So it changed completely from the time we were just finding planets and detecting what they look like in terms of just the structure. Now we're getting really what's inside, what's the physics of this object. And of course, knowing what is inside tells you something about the formation of these planets. Depending on the amount of materials, you know a little bit of the history, as you can guess, if it's from farther away, how it moved. So there is a lot of information to retrieve here. But there is also a lot of careful with all this story, because the obvious steps from here, of course, is trying to think about possibly detect some hint of life, and you really want to detect water, you really want to detect all this, possibly oxygen, all this element that is related to life. I will come back on this. But sometimes we have to be careful about how much we are influenced from what we look at. And I want to go back on a story you may have heard, which I think is a perfect example of things we have to be careful in this whole search for exoplanet. And this, we will see that maybe in the future. There will be a lot of let's say, false alarm or false announcement of something. It's an old story of March. So the guy you have here, it's an Italian, very famous, is Schiaparelli. Schiaparelli is an astronomer of the mid-19th century. What he did at that time is doing a detailed study of Mars. And he produced this map, that was the Schiaparelli map, when he said, well, it's nice, it looks like there is structure on Mars. And if you look back at the paper, he is more careful and say, well, but maybe the structure can come because just it's natural landscape, and it may look like structure, it looked like canals. And that was in the literature, that was said like that, and it stayed like that for some time. And nothing special came up. And then, in French books, there is somebody famous, which is Flammarion. Flammarion, he produced a lot of public books. And there is a whole series. If you go in France, we can find them in flea market. They're very interesting. He produced a lot of books to try to explain to the people the astronomies. And there is one very famous, which is called The Earth from the Sky. When they try the Earth S, it means many different Earths from the sky. You're trying to imagine the other planets, and it goes back to the Schiaparelli picture. And imagine that it's Mars, and then the channels are real channels. That's what he understood. And he put water even into it. This is the Martian version of Flammarion. And this book, it was supposed to be just a general audience book. But then this book was carefully read by this guy, which is Lowell, very famous one. And he said he was deeply influenced by the Flammarion idea. He was reading that book. And when Lowell started up his observatory in the US, he was the one drawing all the canals, you know, the famous Martian canals and all this kind of stuff. And he was so convinced that he has to find it. How he found it, really? And he was so convincing to other people that other people said, oh yes, we also find it. So it was a completely kind of paranoiac situation where they really was so forced to see something that they really did force to see it. And was he completely, then we know it's completely fooled because there is no canal. It's just by luck that the structure looked a little bit like a canal, and it was the big event when they started up with a new kind of telescope and they said there is no canal, and that was the end of the Lowell canal story. But this tells you a lot about the social element into this exoplanet, because it's not only science. You deal with the life, you get with the prospect of extraterrestrial, you get with all that. So you have to be connected to that. So I want to talk a little bit on that, because I think it has an impact, a deep impact on the way the science is done these days. So if you look back to the science fictions about, let's say, between the 20s, 1920 and 1950s, this is what you have. Some of them are very famous. Maybe some of them you saw it. It's the Martian story, of course, because it was the Martians from the Lowell canals. So Lowell influenced a lot all this. It was obvious that would be life, and then there were all these books. And because of the war, of the First World War and the Second World War, people was deeply influenced by this kind of, the Martian has to be very bad, very aggressive. And you all know the story here, the War of the Worlds. And if you read this, it's just before the First World War. And it was extremely bad, extremely negative, and all the influence that people had looking by this was influenced by the complete societies. And then you have to wait quite a lot, a completely change of mind that came up in the 50s and the 60s with the big Apollo program. And we are a generation completely influenced by the Apollo program, with the success of the moon landing, where it was optimistic at that time. Life is to be discovered. Life is to experience. We have to go to space. And it's obvious that all this bad Martian stuff is not the way to see it. We have to be more positive. We have to look to the futures. And it goes to the 60 and the 70. It was part of the way of thinking at that time. And we are very influenced by this yet. We get this perception, I'm fighting personally a lot, that the good science is only done on the other side of the Atlantic. Because of this, because people is influenced by this Apollo kind of program, where when you look at the real productions in science, there is more science done in Europe than in the US. So it's interesting, this kind of social element. And this influenced a lot the way we would look for planet and exoplanet. First of all, it influenced a lot this kind of movie. It's different movies. It's not the same. It's not the bad Martians. So we explore the cosmos. We invade the moon, and then there is a moon camp. And there is a lot of this production. I don't want to dwell into the detail. And then we have a real science experiment that was only possible at that time. It would be impossible to do that today. Like this one, Pioneer. Pioneer is the one that escaped the solar systems. It was bound to visit the giant planets. And there is on this famous plate, you know that. There's a picture engraved with a man and a woman, and then a kind of trick to explain where we are located compared to the quasars, all this kind of stuff. And Pioneer now is sent to the next star, Proxima Centauri. And if you visit JPL, that built this spacecraft, there is a big clock. It's amazing. That tells you when exactly this will come to the next star. So it's a completely different way of thinking. And this was at that time that appeared this idea of the searching for intelligent life. In the 60s, it's Carl Sagan idea, the famous popular book that led to the movie Contact. It's exactly this story with the famous equation, Drake equation, that tried to compute how likely it is that there is other life in the universe. So this is completely influenced by this kind of spirit of the 60s that make this possible. But this had also a dramatic outcome. SETI has found nothing at all, and they have looked for thousands of nearby stars to look for signal that form from the radio. But even more dramatic, maybe those of you that was listening this at that time, is the Marsh Experiments. We sent 2 probes to Marsh, Viking 1, Viking 2. And people at that time was convinced that there will be plenty of life on Mars. It was obvious. It was the optimistic way. So let's send probes, let's try to dig and find microbes, and a lot of excitement. And it was pretty obvious, if you would be a little bit more quiet and relaxed at that time and think a little more, that Mars is a completely sterilized planet because there is no atmosphere, basically. So because there is no atmosphere, the solar beaming sterilizes completely the soil. You know that maybe you can take a bottle of water if you do a desert trip. We can take a bottle of water in a plastic or glass. You put the bottle of water in a sunny place, just a couple of days, and then you can drink the water. It's sterilized. It's because of the sun. So it's completely the case. So you can dig a couple of centimeters on Mars. It's completely sterilized. There will be nothing. And it was in 1977, and it was a shock. And then this completely stopped. It was a fiasco because they found nothing. And it completely stopped the exploration of Mars. That's why there has been nothing for 20 years. It's not the lack of money. There were plenty of money in the 80s. But because of this. So too much, we lose control because we're so much focused by the social element, social influence of this. And we are always influenced by this in these games of searching for planets and searching for life. It was so dramatic that in 1995, the year when we announced the first planet, 6 months before, a team that had started to look for planet, but giant planet farther out, not the one we found, the one like Jupiter, came up with the conclusion that they didn't find any. And then maybe there is no planet. And then 6 months later, we came up with a planet and everything changed. You see how much you can get influenced by all this story. And when we started the program, it was not very fashion to search for planet. In the 60s, 70s, it was, but there are no techniques. That's why they started the SETI. But not in the 90s, because of this story. I mean, people start to doubt about all this. So how come can we maybe one day find life on another planet? Trying to be careful not to fall in the trap of the Viking or in the trap of SETI, or not to be too much influenced by the kind of gloomy ambience that we have these days. So let's look at things at face value here. This is the Earth. Okay, it's pretty obvious. There's a couple of things you do see on the Earth. First of all, the first thing that you may see is water, or the clouds. So the water will certainly be something easy to detect first, because this is the obvious things that you do see on the atmosphere of a planet. But there is something else you have to pay attention to. If you want to play the trick to look at the atmosphere of the Earth, it is very thin. It's very tiny. This is 10 to 20 kilometers thick compared to the size of the Earth, which is about 6,000. It's a very thin layer. And to see this, seeing the Earth is one thing, but seeing something from the atmosphere, it's another game. So it's a tremendously difficult program to try to get into this atmosphere. But let's imagine that someone one day is able to do something here. What will be seen? Well, there will be something that will be very exciting to see. It's getting a spectra. This is a spectra of the 3 obvious objects you want to look if you have a system. You have here Mars, here you have the Earth, and then here you have Venus. So there's a couple of elements that are easy to find in CO2. It's plenty of CO2, so you find CO2. From the depth of the CO2, you know the pressure, you know the temperature, a lot of things you can learn. And there's a couple of other information that's interesting in the case of the Earth. Here you get the water band. It's very special. You don't have water band on Mars. You see it's very flat. You have CO2 as well, very strong, because a lot of CO2 on Venus. By the way, Venus and the Earth are really the same. It's kind of a twin planet. You can even, if you don't know there is an atmosphere, you can compute the thermal equilibrium of Venus, and you find out it's nice to live on Venus. When you put the atmosphere on Venus, you realize, when you measure it, that it's a completely greenhouse run-out effect. It's completely out of equilibrium, and it's like a kind of cover that keeps the planet extremely warm. And that's why you don't have any more water here. And then there is something else that pops up pretty clearly in this diagram, which is here the ozone band. And that makes dream a lot of people. That maybe if we can do that, there is something that we may see. It is ozone. It's something obvious we have in the Earth. Let's try to find it. So what is the consequence of this? Just to make sure we all understand that in terms of life. So I stole a diagram for my biologist colleagues about the story of the oxygen. This ozone is oxygen. It's kind of a state of the oxygen. Oxygen story on the Earth. And it's a kind of a weird scale. Here it's kind of a logarithmic scale. Here it's the beginning of the Earth. It was 4.6 billion years old ago. And then it's like, I used to say it's a human scale. I mean, when you are very young, waiting for your next birthday takes forever, because when you are 5 years old, waiting 1 more year, it's a lot. And then when you are 50 years old, it comes a little bit too fast. So it's exactly the same. So when you look back in the past, you make one step makes a big change. We move from 4.6 to 3. When you come closer here, you need the scale kind of stretch. And when you're in one step, the time is getting shorter. It's called a logarithmic scale. So what you do see here is this is the rise of the oxygen on the Earth, basically because of the photosynthetic way. I used to joke a little bit and to say this is the pollution from the life. I did that one, and there were plenty of biologists, and the guy reacted to say, oh, but life doesn't pollute. I mean, it created the oxygen. So no, I just to be a little bit careful here. So this is the oxygen creation by the life. And this is the amount that we have today, 100%. And you can look back, and you can say, oh, let's imagine we have a look when they were 10% of the oxygen, just maybe enough to be detected. Well, 10%, it was just 1 billion years old ago. But the Earth has been formed 4.5 billion years old ago. So you see the time when we have oxygen, it's not the beginning. It's really a short time. And maybe to detect it, you need 50% or maybe 80%. So it's even shorter. So oxygen doesn't mean that there is no life. You can well have maybe life that do produce oxygen, but you just observe the planet when it is there. So there is so few oxygen that we'll never find it. So you have to be a little bit careful with this oxygen stuff because it's related to the evolution of the life. And the first traces identified of life is close to 1 billion years old after the formation here. It's called close to the older rocks. And it may be connected to this late heavy bombardment I mentioned before. It's kind of 500 million years old after. So this is the first element to keep in mind. So the other one, we have to keep very open about this life stuff because I mean, I appreciate the SETI effort to look for intelligent life and this, but life, come on, it's not someone that sends you a radio signal. I mean, clearly not. I mean, this is something that can end up in many different ways. And let's imagine that you put much more water on the Earth. We don't have continents, so nobody get out on the continent. So we will stay fish forever. So do we really would send radio signal being a fish? It's not very clear. But keep in mind the diversity of life. Please keep this in mind. This is the outburst of the Cambrian. I mean, it was only 500 million years old ago. It's big explosion, completely outburst. A lot of different species, very, very weird. I mean, this is something, it's even better than science fiction and movie. And this is the kind of picture of how we have fossil of this, and this is how we see them. I mean, it's just very fascinating. I got fascinating about this. And they have outside skeleton and all the different kind of shape. And life can be extremely diverse. And that life, at that time, there would not be that much oxygen to be detected. So we have to be a little bit careful here again with all these sociological elements. So about the detections. So let's imagine that then we still can see something and can see some oxygen. What does it mean? How difficult this may be to really tell something about the planet. So to give you a little bit of a feeling without giving a question, I will show you 2 pictures to end this talk. One, it's a very, very famous one. It's called the blue dot picture. It is Pioneer, I mentioned before. They asked Pioneer, when Pioneer was very far above Neptune's, 40 AU from the Earth, 40 times the distance between the Earth and the Sun, to look back to the Earth. It's kind of extraterrestrial picture of the Earth. But this is from the solar system. You're still inside, very far, but inside. The next star, you need to multiply this distance by 1,000 to come to the next star. So 1,000 times this, you end up with the next stars. What you see is very interesting. Well, you do see the Earth. It's here, kind of a dot, a little bit bluish. Interesting piece of information. It's related to the composition of the atmosphere. So I told you we will be able to say something about the atmosphere by looking for the flux, and this is one of them. But then what you do see also is this kind of big, kind of narrow band. It's not a trick from the picture. It is real. It's called the zodilight, or exozodiacal light. If you go in a good site, very clear, just before, after the sunset, before you get the night, you may see this. This is kind of a kind of diffuse layer that's come from all this tiny particle, dust, that is in the solar systems. And because the dust is orbiting a bit the same way than the planet, they're all located in the same plane of the solar system. And this produces this, and because it's tiny, it is heated by the sun. It's basically a piece of, let's say, you can see that at grain, an heated grain, though it produces flux from the thermal emission from these grains. And it produces this, so it may be at some point a problem, because if you keep zooming out, then the point will become smaller and smaller, but the size of this kind of grain will still be very big, and then you may have a contrast problem, and it's called the Zodi problem. You have to fight against all other source of signal you do have. This is just to keep you in mind. And then I stole another picture to a famous French astronomer, which is called Labeyrie. He was always called a visionnaire. He is always 20 years in advance on anyone, trying to create a new optical design and new systems. He was the first one to connect two telescopes together to do what we call interferometry before all the others in a systematic way. And then he has ideas how we may just maybe take a picture of a planet. And he sent me this kind of idea. And this is what we'd like. The idea of Labeyrie, if you are able to build, just to give you the size, a 150 kilometers telescope. So you don't need to have the telescope together. It can be pieces together into space. So it seems a little bit foolish to imagine this today, because the ISS, the space stations, is about 500 meters. This is the best, this is the biggest one we can do. But this, if you do that, this is the kind of picture you could do. And when I got questioned about, well, but you know, it's no way we can do that. Well, I kind of always answer the same. I always say, look, ask someone from the, let's say, 15th century, or ask Christophe Colomb, I said that before, ask Christophe Colomb whether you think we could just cross the Atlantic in 7 hours. Just relax. Flying like a bird. So maybe he would have tell you it's crazy. No way. But then we're doing that very often. Just cross the Atlantic, you fly, it's very relaxed, you get a glass of wine. So it's extremely difficult to get a picture of the far futures. As far as there is no strong limitation from the physics, like you want to break the speed of light, or you want to do something that really violates some fundamental law of physics, there is nothing that prevents us that one day this is the kind of picture we'll be doing. And then if you do that, well, you may see continents, you may see forest, if there is forest, and then we may look back to this kind of very kind of pioneer work that we are doing here and these days with a lot of other people. We're just starting, I think, a big new kind of problem, questions that will lead one day to this. And I won't see that, but I'm sure the future generation of students will look to see that. So I will end this talk with this kind of very futuristic picture and wish you a good evening.